So now let us look at let us look at this. Now every time we study a fluid, okay, we use two concepts, right? So one is this, the Lagrangian concept, okay, and the Eulerian concept. Okay. Now, what do these two things mean actually? Okay. Now, based on this, I'm going to try and explain to you, what we're looking in terms of the velocity. Now, how do I explain this? Now, the Lagrangian concept. Okay. Now, for example, right, you have a movie theater or say a classroom, okay, or a room basically where people are streaming in for various meetings. Okay. So, say you have a door, right, you have a door like this, okay, and you have people walking in, all sorts of people are walking in through this door, right, and there is somebody here, this person is sitting here, it could be a teacher or somebody who is sitting there who's watching. Okay. Now, if this somebody is constantly just watching the door, right, is just watching the door, okay, is watching the door and just noticing the number of students who walk in and what is happening at every second and how many people are walking in which direction they are going, but he is all focused on this location x naught, right, that is all he is watching. So, then this is essentially the Eulerian concept. Okay. On the other hand, say this person looks at this person called A, and A walks in, right, A comes here and then A follows this path and goes here and moves here and then goes somewhere here finally. And this person is constantly watching all this. What he is doing is he is following this person A start to finish. Right? And this is the Lagrangian concept. Okay? So, if this is a Lagrangian concept, so based on that, okay, as we are going to look at a velocity. Okay, based on this, we are going to look at the velocity of a particle, something like this. So, where it is, so how can you calculate, or how can you calculate or how can you evaluate a motion based on this kind of a concept. And total derivative, the concept of a total derivative is something which is important from this point of view, right. Now, both these concepts are used depending on your specific need. Okay. Let us look at this. This is a very interesting thing. So, now so we're going to call this y and z. Okay. So, if you're going to do that, now say we have a fluid element. Now, say we have a fluid element, right, which is here, and it moves to some point here. We're not exactly concerned about the path. So, however, so it could be basically any path, right? It could be anything really. So, let's just say that the velocity here is v1. Okay, its velocity here is v1 and velocity here is v2. Okay, and this location is actually x1, y1, z1. Okay, x1, y1, z1. Is that too? Okay, sorry. So, let's rest that. So, this is essentially x1, y1, z1. Okay, and this location is x2, y2, z2, and this time is t1 and this time is t2. I could have actually put this t1 alongside this, which essentially means that the velocity is a function of space and time. So I can write that as x, y, z, and t. So essentially what I'm saying is that we are looking at a fluid element which is moving from, say, position, let's just say position 1 to 2, position 1 to 2, in a way where the velocity depends on both space and time. Okay, now if which is what it is, right? Now what we're going to do is just look at the x component for a change. So what we're saying is, right, we're going to just look at x, right, and this is nothing but v, right? Now so it's moving from x1 to x2, so this is essentially, so this is nothing but, this is x1 and this is x2. Okay, so and it is v1 here, right, and here it is v2, here it is v2. Okay, so if I do this, right, if I do this, so here the value is v1, at x2 the value is v2, right. So this is essentially the change of the velocity with respect to x. As we go with respect to x, then how the velocity changes, right. So in here, so let's just say that this is theta, right. So all we're going to do is find out the slope of this curve, right. So tan of theta is v2 minus v1 by x2 minus x1, right. So slope of this curve, right, slope of this curve is what? Is basically dv dx. Note I write a partial here because this velocity will depend on y and z as well as t, right. So I write a partial, so it depends on x as well as y and z and t. Okay, so slope of this particular curve, where we are looking at the change in velocity only with respect to x, so is del v del x, right. So then what we'll write here, so therefore what we can write is it's just simple math. So del v del x is v2 minus v1 by x2 minus x1, right. Or can I write delta v, right, delta v is equal to del v del x into delta x, right. Now if you see, basically what I'm saying is I will write this as delta v by delta x, right. If I do that, then I can write delta v to be equal to del v del x into delta x, right. So so similarly, so this basically you get for the x direction, right. So similarly we can write it in the y direction and z direction. So what we say is, so this thing is essentially direction in the so this I can say, so let's put a subscript here, say x. So then delta v, sorry, okay, so then we can, okay, let's write it here. So delta v, okay, y is nothing but del v del y into delta y, right. So that is for y direction, and delta v in z direction, right, is del v del y del z. Okay, this is, let's call this, so change in the velocity in the x direction, change in velocity in the y direction, change in velocity in the z direction, and similarly is also the change of velocity with time is basically del v del t, right? Let's put that. So therefore, what we see is that as the particle moves from position 1 to position 2, the velocity is a function of both space and time. So therefore, I can write down the changes in space, so that is defined by x, y, and z coordinates as this, and the change with respect to time by this. Therefore, let us now write, okay, the total change in the velocity. So if we have to do that, so what is the total change in velocity? So this is nothing but the total change in v, right? So that I will write as, say, the total change in v. So that is del v del t, right? Del v del t, right, is happening over time, delta t, right? Then plus the total change in into delta x plus del v del y delta y, right, plus del v del z delta z, right? If I do that, right, then what I'm going to do is take the delta t out, divide throughout by delta t. Then what we get here, as you can see, okay, let me just do that, and I'm going to just a second, okay. So what I'm going to do is erase the t from here, okay, and then just save my time a little bit, and I've got to divide by delta t, right? So if I do that, right, and then what I'm going to take is limits, right? I'm going to take limits, and I'm going to say that limit delta t tends to 0, and that is for the entire case. So if that is true, then what happens? So what that essentially means that this is an acceleration, right? This is an acceleration, but we're going to write this. If you look at this delta v by delta t has quite a few components, right? It's not very familiar to what you've known earlier, right? So this, we're going to actually write this as dv dt. If you haven't come across this earlier, so this is what it is. So we're going to write this. In this case, the total change in velocity, right? So if I do that, and then that is equal to del v del t plus, now what is delta x delta t? Limit tends to 0. That is by definition the x component of velocity, right? So I will write that as del v del x plus v del y plus w del v del z, right? This is what it is, and here essentially, so this bit is called a substantial derivative or total derivative. So this is nothing, this is essentially, it's called several things: substantial derivative or total derivative, right? Now this is what? So this is essentially, in this particular case, we are looking at the total change in we're looking at the total change in velocity. So this bit is the local acceleration, instantaneous acceleration. So this is essentially the local derivative, right? This is the local derivative, okay, and this is the convective derivative. Why is this happening? This is happening because the fluid, this sort of a thing arrives only in a fluid, right? This sort of a thing, this sort of a change will happen only because it's a fluid, because the particle, the velocity is changing as the particle is moving in space. So there is an acceleration, right? This is more familiar, you're probably more familiar with something like this. The acceleration is rate of change of velocity, which is instantaneous, right? So that as you change time, the velocity changes, right? But this, if you look at here, there is no time here, right? Except the fact that during the passage of the time, the fluid particle itself is also changing its location, right? And because of that, there is this convective acceleration. So it is convecting. It also comes from there. So this is nothing but convective derivative, in this case acceleration, right? Now a very simple example to sort of so I started off with this in the sense to explain what a substantial derivative or a total derivative, or it's also called a material derivative. It's also called material derivative. Okay. Now I'll give you a very small example. Now you could have a candle, right? You have a candle, you take your finger, right, and you move it very swiftly across the flame, right? You move it. So this is my candle. I move the flame, and there's a flame, and I take my finger and move it very quickly across the flame, right? So you feel that pinch of heat. So that is nothing but local derivative of the temperature. So if you, for example, say you had, this is your candle flame, right? This is my artwork. Okay, I'm sure you can draw better than me. So this is my candle, right? So now if I take my finger and move it very quickly across the flame, there is that rapid change in a wee bit of change. You feel a little heat, and that is nothing but this change of temperature over a small instant of time. And then what I do is I take my finger, okay, and dip it into a big box full of ice. I take it in a big box full of ice. I dip my finger into it. So here basically then the heat that I feel, that slowly goes away. The heat is being basically, the heat therefore flows. The heat flows from the hot source, which is your finger at this point of time, to the cold source, which in this case is this bag of ice or box of ice. So this here is the convective acceleration. So this here is essentially a convective acceleration. Okay, so this we could actually yeah, so that is that. Now the reason I started with this, because I was going to go and talk about the basic, so something called a Reynolds transport theorem. Okay, I was going to talk about that. So I sort of introduced this substantial derivative. Okay, now let us, so for any fluid flow, okay, let's let us say B, this we will denote, which is any extensive property. What is so it is an extensive property. I hope this is okay. So it is extensive property. Yeah, okay. Extensive property. Okay. So like mass, momentum, energy. Right? So these are an extensive property, and an intensive property is nothing but B per unit mass. Okay? So B per unit mass. So this is something that we have. Now I hope that you understand what a control volume is. Okay? So yeah, so I'm not going to go into details of what a control volume is. So in case you you need to remind yourselves, please do. Okay, I'm going to not go into kind of the basics of that. So that's the control volume. Okay, now for example, I'm going to do this very simple. Okay, now I have basically okay, a system. I'm going to talk about a system, right? And this system moves from one position to the other, you know. So a system basically would consist of a large number of system would consider of the fluid particles that we just talked about. We talked about a little small particle which moves from one point to the other. But most of the time for studies in fluids, right, think of an ocean where you're trying to study the force generated by a ship. Now, you're not going to be concerned about how one fluid particle is moving from here to there, right? But what you're going to be concerned about is essentially a big, you're going to consider a big, mass of fluid, right? And you're going to concern about those particles of fluid all the time as to how they are behaving because of the movement of the ship. And that exactly, and so which mass of fluid are you going to consider, which group of fluid particles you're going to consider is what is the control volume. But anyway, do remind yourselves what that is, okay? So let us look at this. So we're going to consider, say, a control volume, like that. We're going to consider a control volume. Okay, and this is fixed, right? This is a fixed control volume, right? This is a fixed control volume. Now, then, okay, my system comes in, right? Now, the system coincides, so my system basically coincides with the fixed control volume at time t. Right. So this is the system at time t. So I'm going to draw over this. So basically this is my system. So my system actually coincides with the fixed control volume at time t. Right. The system, however, moves, it moves, and there is still some overlap, however, but it moves. Okay. So the system is here. This is my system, right, at time t plus delta t. Okay. So let me call this area, this unshaded part, let me denote that as 1, and this part, the shaded part between the red line and this one, let me call that as 2. Okay. So incoming is basically, it comes in with the velocity v1, goes out with velocity v2, right. This is the system. So therefore, so the extensive property of the system, right, at time t is equal to the extensive property of the control volume, because it matches that. Okay. So then of the system at time t plus delta t is what? Is, if you look at this, basically I'm trying to look at this area is nothing but this whole control volume, right, minus 1 plus 2, right. The control volume is the red part minus the unshaded part 1 plus 2 is this extra part. So it is control volume at control volume at t plus delta t doesn't matter, it's still t plus delta t, it is fixed. Basically, it does not matter, okay. Minus 1 minus B1, okay, at t plus delta t plus B2 at t plus delta t. Okay. So, if we do this, okay, if we do this, so then I am going to skip a couple of steps because this is a derivation. I am going to do that. So, what I am going to do is 2 minus 1, okay, by delta t. Okay. I do that and then also take the limit that delta t tends to 0. So, if I do that, then what I basically get is d dt of B system is nothing but d dt of B control volume minus rate of change of the extensive property in 1 and 2. Okay. Now, I will just right now, like we are going to just write this. Okay. Now, if you look at this, this is the extensive property over 1 at time t plus delta t, right. Now, this I can write as B, right. Let me call this as B1, right, and say M I t plus delta t, right. So, it is nothing but because extensive property is intensive property into the mass, isn't it. So, that is by definition what we wrote earlier. Now, this mass thing, okay, the mass I can, I can break this down. So, I can write this at this, okay, it is 1 rho 1, okay, then velocity 1 t plus delta t. Okay. I can further break this down and bring it into area. So, B1 rho 1 V1 delta t into A1. Okay. So, therefore, if I do that, okay, if I do that, then okay, limit delta t tends to 0. Now, B1 t plus delta t by this, right, is equal to what? Is equal to nothing but B1 rho 1 V1 A1, right. So, this is this. So, this is nothing but incoming extensive property, the rate of incoming extensive property. Similarly, on similar lines, so limit delta t, this is this delta t by t. So, I am not going to write that. This is nothing but rate of extensive property which is going out. So, therefore, what we can basically say is that D system, right, is equal to control volume dt minus B in rate plus B out. Okay. So, let us keep that. Okay. So, therefore, the rate of change of property B, right, the rate of change of property B of the system is equal to the time rate of change of B of the control volume, okay, plus the net flux. If you see the net flux of the B out of the control volume of the mass which is crossing the control surface. Okay. So, let me just sort of write down a little bit. Okay. So, time rate of change of property B, right, of the system, right, is equal to rate of change of is equal to rate of change of property B of the control volume, right, plus net flux of the property, net flux of the property, right, out of the control volume, right. This is CV basically, control volume, okay, control volume. So, I will go a little bit, just a little bit. So, this has a very interesting form which which one can use. Actually, it has a very inlets and outlets. You can essentially sort of use that. Okay. So, so this B net, right. So, this B net, let me just write this out, is nothing but B out minus B in. That is the rate, right, that is the rate, and this I can write out as from the control surface, right, rho B V dot N dA, and this N is essentially the directed vector out of the area. It is an area normal basically. Okay. So, this is it, and I can actually write this down. Okay. I can write this out to be the number of inlets and outlets. Okay. I can write this out as the number of inlets and outlets. So, this one I can actually break it down, I can sum it. Okay. I is equal to 1 to say n. So, rho I B I V I N I, okay, A I. Now, so let me just do that. Okay. This is A I and this is V I. This is an inlet. This is an inlet, right. This is AI and this is VI, this is an outlet. Okay. So, therefore, what we are basically saying is that for an inlet V dot actually for inlet VI, okay, dot N is equal to this, and for outlet VI dot N is VI. Verify this yourself, convince yourself that what I am saying is right here. Okay. Do not just believe me just like that. Okay. So, therefore, it will automatically take care of it. So, if for inlets this will become negative, for outlets it will become positive. That is how the directed normal is all about. Now, so having said that essentially, so therefore we can write the, so we have written the Reynolds transport theorem, right. Let us see what we wrote back. I will just go back to check that, or yeah. So, therefore, this is what we came up with the Reynolds transport theorem. Okay. Now, all we have to do is, if we use in this case, if the B system, the thing that I consider is mass, if I do consider mass, then what I get out of the Reynolds transport theorem, okay, this is named after Osborne Reynolds. Okay, so if you do that, then what you get is essentially the conservation of mass. Then you can add to it the conservation of linear momentum. So if B system is momentum, then what you get out of it, out of the Reynolds transport theorem, is essentially what you get out of it is essentially the conservation of momentum. Okay. So I think you can sort of do this yourself. So for example, let me just quickly do this and we'll close. Okay. So for example, we're going to use this, right? We're going to use this. If you're going to use that, right? And this total flux is something that we're going to replace by the summation that I just said. So this is basically total flux and out of total inlets and outlets, and the remaining will remain same. So then, so essentially dB system dt is dB control volume dt, right? So if I do that, so and let's say B system is mass. So then if I do this is this, right? dm dt, and this is equal to ddt, okay, rho B, okay, rho B dV, this is volume by the way of the control volume, right, plus summation of I is equal to 1 to n. So rho I B I Vi dot Ni Ai, right. If I do that now for a steady state case, right. So if for a steady case, right, what happens? So if I have a steady case, this shall go to 0. Okay. Now since in this case m, so therefore we're talking about this, so this is equal to 1, right, it's equal to 1. So therefore what we get out of here, is very interesting. What we get essentially is I is equal to 1 to n, right, rho I Vi Ni Ai is equal to 0. So we sort of get that, okay, and we can, so in this case you could actually write, say, if the number of now you see here, okay, now this rho V and A, okay, plus or minus, this becomes minus for inlet, plus for outlet. So this rho VA, right, so this is nothing but mass flux, right, this is nothing but mass flux, we know that already. So therefore what is basically is saying that the total mass flux is 0. So you can actually sort of even write this down in this way. So this is nothing but mass flux, and that again across the control surface, so rho V dot n, right, dA, right, and that is equal to 0. Okay, that's what essentially is what we get. Okay, so I think we'll kind of stop here. Okay, so this is the brief understanding that I thought I could brush up, and we will start basically from the understanding, begin with concepts of boundary layers right from the next module. Okay, so we'll stop here and pick it up directly with the boundary layer. Okay, thank you.